Any unauthorized reproduction, use, transmission, or delivery of the materials contained herein, in whole or in part, without the express written permission of Educational Activities Video Incorporated, is forbidden by law and subject to penalty.
Ever go stargazing?
In space, our home planet is just one of countless heavenly bodies, among many stars and galaxies in a boundless universe stretching across billions of light years.
While here on Earth, we have another universe. This one formed by the countless particles that make up matter.
This micro-universe, existing in the things all around us, is being constantly explored by chemists. Atomic theory and the periodic table. The basis of our modern life, how we live, depends on both scientists and people like ourselves understanding the nature of matter, or, in other words, what makes up the world around us.
Indeed, in our daily life, the great benefits and advances in food, clothing, medicine, communications, and building structures depend on our understanding of chemistry.
The pharmacist responding to your medical needs, an engineer designing bridges, the medical researcher striving for cures, or the computer scientist designing the latest microchip. All utilize chemistry to improve our lives and help determine our future well-being. For all these people, chemistry is the critical underlying science that links all branches of science.
In this program, we'll begin by taking a look at atoms, the particles that serve as the building blocks of matter.
Next, we'll discuss one of scientists' most important tools, the periodic table, which provides a kind of blueprint for the changing world around us.
And we'll review the main groups or families of elements that make up that table.
First then, let's discuss atoms, the particles that chemists call the building blocks of matter. Matter, as you'll recall, makes up the many things around us, such as the clothes you wear, the food you eat, the chair you sit on, and the desk you use. In short, matter is anything that occupies space and has mass, and exists in four basic states: solid, liquid, gas, and plasma. In a sense, all scientists are similar to detectives trying to solve life's mysteries. For centuries, the great puzzle challenging chemists has been, what makes up the world around us? What is the composition of matter? Indeed, it has taken chemists more than 2,000 years to unlock the secrets of the micro-universe that exists all around us, so that they can understand the small particles that comprise matter.
The search started some 2,400 years ago with the Greek philosopher Democritus. A thinker well beyond his time, Democritus proposed a theory that all matter is composed of small particles he called atomus. But it wasn't until 1808 that English chemist John Dalton further developed the idea of Democritus into what is now the atomic theory. In fact, the atomic theory has become the foundation for modern chemistry and science, so that today scientists consider atoms the building blocks of matter.
Atoms, of course, are very small. So small that the thickness of one thread from your shirt or sweater contains hundreds of thousands of atoms. Each atom has a center called a nucleus. Compared to the entire atom, the nucleus is very small. How small? Well, chemists suggest that to imagine the size of a tiny nucleus in an atom, we think of a marble in a large football stadium, like the one we see here. In turn, an atom's very tiny nucleus contains two major particles, a proton and a neutron. Protons are positively charged particles located in the nucleus, while neutrons are electrically neutral. All protons are identical, and all neutrons are identical. Surrounding the nucleus in an atom is mostly empty space. But here, moving around the nucleus, we find negatively charged particles, named electrons. These three tiny particles, the proton, neutron, and electron, that are part of every atom, are called subatomic particles. A proton and neutron have about the same mass, both very small. But an electron is still far smaller. Scientists tell us that the mass of an electron is only 1/2000th of a proton or neutron. But chemists say that despite this difference in mass, the positive electrical charge of a proton is equal to the negative charge of an electron.
In the early 20th century, scientists continued to forge ahead in their exploration of the micro-universe of matter. Striving to understand the particles that make up matter, the Danish physicist Niels Bohr developed a planetary model of the atom in 1913. Given this perspective, the planets circling the Sun in the solar system serve as a model for the subatomic particles in an atom. So in every atom, we have protons and neutrons in the nucleus, and electrons moving around the nucleus. The electrons, however, don't move in fixed paths, and they circle the nucleus billions of times every second. Whirling around the nucleus, the electrons move in paths that are arranged in energy levels, with the lowest energy electrons found near the nucleus, and the higher energy electrons circling farther from the atom's center. We know that atoms are different depending on the elements they're part of, and that all protons are identical, as are all neutrons. Considering these facts, then, what do you think distinguishes one atom from another?
The distinguishing factor lies in the particles in a nucleus, or more specifically, in the number of protons that exist in the nucleus. For instance, take the atom of carbon, which has 6 protons in its nucleus. A dark solid, carbon makes up most of the burned wood we see here. While on the other hand, nitrogen, with 7 protons, has just 1 more proton than carbon. And nitrogen is a colorless gas that's all around us, making up most of the Earth's atmosphere. So the number of protons in a nucleus determines what the element is, whether it's carbon or nitrogen, or perhaps aluminum or gold. Each atom, then, has what chemists call an atomic number, which refers to the number of protons in the nucleus. The concept of an atomic number was first developed in the early 20th century by a British chemist, Henry Moseley, who used X-rays to differentiate the nucleus of different elements.
Let's take a look at this chart. The element carbon, for example, has 6 protons, thus giving it an atomic number of 6. And the element helium has an atomic number of 2. so the number of protons in its nucleus would be 2. The model for atomic numbers also takes into account the number of electrons in an atom, reasoning that since atoms are electrically neutral, the number of electrons in an atom will be equal to the number of protons. Let's look again at the carbon atom, where the atomic number is 6, which indicates that the number of protons in the nucleus and the number of electrons in orbit around the nucleus are both 6. Now consider this. If the element aluminum has an atomic number of 13, how many protons and electrons does an atom of aluminum contain? Remember, because an atom of aluminum is electrically neutral, it must contain exactly the same number of electrons as protons. That is, 13 electrons and 13 protons.
Since atoms contain protons, neutrons, and electrons, it is logical that atoms must have mass. Indeed, the mass is very small, but chemists have developed the technology to measure the mass with great accuracy. While the nucleus is tiny, it holds 99.9% of an atom's mass, and scientists define the mass of an atom as the sum of the number of protons and neutrons in an atom. In this figuring, electrons are not considered because it would take thousands of electrons to equal the mass of one proton or neutron. So in other words, the mass of an atom equals the number of particles in the nucleus of that atom. Let's look at the carbon atom again. The letter C is the symbol for carbon, whose nucleus contains 6 protons, giving carbon the atomic number of 6, with 6 neutrons also in the nucleus. Since the mass of an atom is equal to the sum of protons and neutrons in the nucleus, the atomic mass of carbon is 12.
Now let's consider the element sodium, which has the chemical symbol or shorthand Na. How many protons appear here in the nucleus? And how many neutrons are evident in the nucleus? Now, based on this information, what is the atomic number and mass of this element? As we've demonstrated before, the atomic number is equal to the number of protons, giving sodium the atomic number of 11. And the atomic mass is equal to the sum of the protons and neutrons in the nucleus, which means that sodium, with 11 protons and 12 neutrons, has an atomic mass of 23.
Everything on Earth and in space is made of atoms. But since regular microscopes are not powerful enough to view these minute particles, scientists must use special instruments to study atoms. In 1981, a new kind of electron microscope was invented that can magnify objects up to 10 million times. Called the Scanning Tunneling Electron Microscope, this instrument enables chemists to actually see atoms. Scientists also use lasers to slow rapidly moving atoms so that they're easier to study. And with a machine known as the Super Collider, scientists are able to force protons to collide at nearly the speed of light. Detectors and computers record the particles produced by the destruction of the protons. Through this process, scientists hope to better understand how the atom is constructed. Utilizing these and other methods, scientists continue to gain valuable data about atoms, the tiny particles that serve as the building blocks of matter. Now, for a review question, go to activity sheet number 1.
The element phosphorus, along with the element calcium, is an essential ingredient in dairy products and helps to build strong bones and teeth. The average atomic mass for phosphorus is 31, but the element also has a highly radioactive form with an atomic mass of 30. What are two reasons to explain why most of the phosphorus in our food supply is phosphorus 31 and not the radioactive form, phosphorus 30? Turn off the player to answer the question, then turn it back on when you're finished.
Here's the correct answer for the exercise you've just completed. Since the most naturally occurring atom of phosphorus is phosphorus 31, this form of the element would be most likely found in nature and in your food. Remember, phosphorus is a nutrient that living organisms use along with calcium to build strong teeth and bones. In fact, living organisms could not survive if the element's radioactive form, phosphorus 30, were in our food supply. We have now reached the end of part 1 of the program. You may turn off the player or continue the program if you wish.
With our study of atoms as a basis, we can now discuss one of science's most important tools, the periodic table. In the late 1800s, scientists were making great strides in understanding the nature of matter. But chemists wanted to organize their data, specifically the elements, in a logical manner for reference and research.
A brilliant Russian chemist, Dmitry Mendeleev, arranged the atoms of all elements in the order of increasing mass. He had observed that certain atoms had a pattern of properties that was very similar, and that this pattern repeated itself periodically. The Russian chemist called the listing a periodic table. But there were gaps and inconsistencies in this 19th century table, and it took some 50 years before the British scientist Henry Moseley clarified the listing. After Moseley determined the atomic number of elements, chemists reorganized the periodic table so that elements, instead of being arranged according to atomic mass, are listed in order of increasing atomic number.
To refresh your memory, once again, what is an atomic number? An element's atomic number is the number of protons in the nucleus of each atom of that element.
Once reorganized, the table was more efficient, as elements with similar properties fell into logical order. The modern periodic table looks like this, and is based on the periodic law, which states that properties of elements are the periodic functions of their atomic numbers. That is to say, the physical and chemical characteristics of elements result from their atomic numbers, as shown in this listing. It may help you to understand the periodic table if you think of it as the vital, streamlined database for chemists, developed before the existence of computers. Because the periodic table of elements is unquestionably one of scientists' most important tools, classifying, like a library, a great amount of information in a usable, logical way. The table serves as a framework for the atoms of elements, the building blocks of matter in the world around us. As such, this listing represents the unfolding story of our daily life. Here, we can see at a glance the elements that are the foundation for the matter that makes up our planet. And indeed, the periodic table provides a kind of blueprint for the constantly changing world around us, because the physical and chemical properties of these elements are the basis for the medicines, products, goods, structures, and natural environment we enjoy now and will experience in the future.
Let's take a look at the elements in the periodic table, which is not nearly as complex as it first appears. There are 109 known elements, and each one of these elements is described in a separate box. Take the element magnesium, which we see represented by this box in column 2 of the table. The large letters Mg are the chemical symbol for magnesium. The smaller number at the top of the box, which here is 12, refers to the atomic number of the element. The larger number refers to the atomic mass. As for the numbers to the right of the decimal point, we'll discuss those in a moment. So using this example as a guide, you should be able to obtain information about every element in the periodic table, including the element's symbol, its atomic number, and its atomic mass. All of the elements, of course, serve a purpose in our practical lives. Magnesium, for instance, is an element found in compounds used for airplane parts, in medicines, and even in fireworks, among other things. So based on the table and some additional information, you can learn what the properties of an element are. That is, ways in which the element is currently used, and possibly what some future uses may be.
Now, let's consider the element potassium. According to this box from the table, what is the symbol for this element? What is the atomic number for potassium? And what is the atomic mass? According to the table, the symbol for potassium is K. The atomic number is 19. And the atomic mass is 39. The element potassium, incidentally, is found in compounds used in fertilizer and also in photography. Based on the information in the table, we can now draw the nucleus of a potassium atom. So, draw a circle representing the nucleus and calculate the number of protons and neutrons in the nucleus. In your drawing, represent the protons with a plus symbol, standing for a positive charge, and represent neutrons with a plus-minus sign to show they are neutral. Go ahead now and draw the nucleus for a potassium atom. Your nucleus should look like this, with 19 protons and 20 neutrons. Can you infer, that is, figure out, how many electrons this atom has? Since atoms have a neutral electrical state, the number of positive charges must equal the number of negative charges. So, if an atom has 19 protons, it will also contain 19 negatively charged electrons.
When you use a pencil, you're able to write because of graphite, which is mostly composed of the element carbon. There are so many carbon compounds, in fact, that an entire branch of chemistry, organic chemistry, concerns them. Chemists, however, have determined that many elements, including carbon, have atoms that are not always the same and are sometimes unstable. This difference between an element's atoms and the resulting lack of stability occurs when there is a difference in the number of neutrons contained in the atom's nucleus. In this artwork, for example, we see the structure of an atom's nucleus. How many protons, represented by the red balls, does each nucleus contain? As you can see here, there are 6 protons in each nucleus. because 6 is the atomic number of carbon. But now, look at each nucleus again. How many neutrons do you see? In one nucleus, you have 8 neutrons, while the other has only 6 neutrons. So in one atom, we have an atomic mass of 12, and in the other, an atomic mass of 14. Thus, atoms of the element carbon exist in 2 natural states, as carbon with a mass of 12 and carbon with a mass of 14. Chemists use the term isotopes for such atoms of the same element with different numbers of neutrons, a state that results in a different atomic mass.
Now, back to the periodic table, where you can note that the atomic mass for carbon is stated at 12.011. Now that you understand about isotopes, can you explain why the atomic mass for carbon is written not as 12 or 14, but as 12.011? Since both forms of carbon exist in nature, chemists have found a way of determining how often one isotope exists as compared with the other. The number 12.011 is actually an average atomic mass. This number indicates the average mass of the mixture of its isotopes. Isotopes of elements often have different properties. Take iodine, for instance, an element we've all used in medicine. Iodine usually has an atomic mass of 126 and is very stable. But there's an isotope of iodine with an atomic mass of 131 that is unstable. What happens with this isotope? The neutrons in the nucleus rearrange themselves spontaneously until the atom reaches the stable form of iodine. And as the nucleus stabilizes, energy is released in the form of radiation. Chemists say that unstable atoms like this are radioactive. How have chemists harnessed such radiation to benefit people? Well, the radioactive form of iodine can be used for effective medical treatment, because in some cases, a person's thyroid gland can develop a tumor that can be destroyed by the radiation from the unstable isotope of iodine. So a carefully controlled treatment can kill the cells of a tumor while not harming healthy cells.
Having discussed the history and meaning of the periodic table, let's now consider some of the main groups or families of elements represented in the table. The table is precisely designed to include 18 vertical columns of elements, called groups or families. Within each column or family, elements have properties that are similar but not identical. Thus, in column 11, we have the elements copper, silver, and gold, all similar but not identical metals. Each horizontal row of elements in the table is called a period. Here, for example, we have a period including the elements iron, copper, and zinc. Each is a shiny metal and a good conductor of heat and electricity. To the left of the step-like line in the table, all the elements, with the exception of hydrogen, are metals. Metals like coins, kitchenware, and steel girders are very much a part of the advanced industrialized life that we enjoy. Metals share some common characteristics. Can you name some of them? Most metals are shiny like this gold, solids at room temperatures, and good conductors of heat and electricity like this copper tubing.
To the right of the step-like line in the periodic table, we have nonmetals, such as the oxygen we need to breathe, carbon, and iodine. Think for a moment. What are some of the characteristics shared by nonmetal elements? At room temperature, nonmetal elements are usually gases, like the neon in these red lights. Or some elements, like sulfur or carbon, are brittle solids and do not conduct heat or electricity well. In groups 3 through 12 of the table, you find families called transition elements, which have properties between those of metals and nonmetals. Such is the case with silicon, which is classified as a semiconductor or semi-metal. Silicon and other semiconductors play a vital role in computer technology.
Finally, the periodic table contains a certain number of synthetic elements with an atomic mass greater than 92. Such synthetic elements are man-made and do not exist in nature.
Let's review for a moment now what we've covered in this program. First, we studied atoms, which chemists call the building blocks of matter.
Next, we discussed the periodic table, chemistry's unique blueprint for the world around us.
And finally, we looked at the groups or families of elements that are precisely classified in this remarkable table.
Indeed, learning about this table heightens our awareness that our world is made of matter comprised of the atoms of elements, and that in various ways each of the elements in the periodic table is part of our lives.
To review the material we've covered, here's a final question for you to answer. Your teacher will discuss the answer with you after the program. Turn to activity sheet number 2, and we'll take a look at the question now.
A sample of the element silver contains 60 atoms, with each of them having 61 neutrons. In the same sample, there are another 40 atoms, with each containing 62 neutrons. How would you determine the sample's average atomic mass?
Go ahead now and complete the program. Later, you can discuss the answer with your teacher.